Let's take a look at this example from section 4.4. This is a section that deals with the connection between graphs and derivatives. And we're going to work our way through step by step some of the different items that are suggested to focus on when you are using derivatives to understand graphs. Some of these things actually come from pre-calculus, so do not involve derivatives, but they're all part of getting a comprehensive look at some of the main features of a graph. A natural question to ask here is, why not just use a graphing calculator? Why not just use technology to get our graph and forget about all this, derivative stuff that is sort of a slower process? But here's what I want to say about that. If you are too dependent on technology to give you these answers, the problem becomes that you lose the ability to think about whether the answer that you're getting from technology makes sense. So you are totally reliant on whatever the technology tells you the answer is, and have no way of sort of checking whether maybe you entered something incorrectly and the graph doesn't make sense. But if you can't recognize that, then you're just going to accept whatever your calculator or your graphing utility tells you is the answer. So that's what I would say is a danger to avoid, is becoming too dependent on whatever the calculator tells me. I'll just accept that without being able to independently sort of evaluate whether it makes sense. The other thing is, of course, we've been looking at these derivative rules, and we want to see how derivatives are used in some of the applications, and this is an important application of that. So let's take a look at this example. We have this rational function x squared over x squared minus 4. This section of the book lays out 9 different items of things to look at. I don't want you to think that I'm going to ask you to go through 1 through 9 and label them as such and so on. Some of these are not relevant to every example. Some of them may not be particularly helpful in understanding how the graph of a certain example looks. Okay, but generally you're going to want to look at most of these things and understand when they're applicable and when they're not. So domain is one thing. Certainly when you look at a rational function, there's potentially things that are outside the domain because they would cause you to divide by 0. In this case, plus or minus 2 are not in the domain, and in interval notation we could express that domain this way. Symmetry. Symmetry is a good example of something that not every single example is going to have the symmetry of an even function or an odd function. There are plenty of examples that are neither. This happens to be an even function. And again, what makes a function even is that f of negative x is the same as f of x for every x in the domain. That's true here because we're squaring x in both the numerator and denominator. So changing the sign of x is not going to change the output. And so that means it's going to have symmetry about the y-axis. We'll keep that in mind as we go through the rest of this example. Finding the first and second derivative. So here's the part where derivatives come into play. The quotient rule is involved here. I left out some steps of algebraic simplification. You do want to simplify the first derivative before you take the second derivative, just to make things easier for you. Critical points are places where the first derivative is 0 or undefined. In this case, the only places in the domain, remember plus and minus 2 are not in the domain, the only places in the domain of this function that are critical points is just x equals 0. If we look at the sign of the first derivative, well, that denominator is always non-negative, okay, or in the domain is always positive. So the sign of the first derivative is determined by the sign of the numerator. And the numerator is positive when x is negative. The numerator is negative when x is positive. So we've got an increasing function f of x when x is negative, decreasing when x is positive. That'll be another thing to keep in mind when we get to the graph. Concavity, the direction of concavity is determined by the sign of the second derivative. And similarly, we can look at this and say, well, that numerator, no matter what x is positive. That numerator is positive. So the sign of the second derivative is determined by the denominator. And what we conclude, based on where it's positive, is that the original function is concave up when x is greater than 2 or less than negative 2. And based on where this is negative, we can say this will be the original function is concave down between negative 2 and positive 2. Okay. Inflection points. Inflection points are places where the second derivative changes sign. Okay, or to put that in terms of the original function, it's where the original function's concavity changes from up to down or down to up. The places where the sign changes occur with the second derivative are at negative 2 and positive 2. But those are not in the domain of f, so we have no inflection point. The first derivative test would tell us we have a local maximum at 0, and that's the only local extremum. And that's because at 0 is where we see this transition from an increasing function to a decreasing function. And that's the only place where the first derivative changes sign. Vertical asymptotes, negative 2, positive 2. Horizontal asymptote, remember how we determine that when we're looking at a rational function. Here we have the same degree in the numerator and denominator. So the horizontal asymptote is y equals 1 based on those leading coefficients. Finally, the only intercept is 0, 0. If we put all of that together, we get a graph that looks something like this. Okay, we've got, it's increasing where it's supposed to be, it's concave down here, concave up here. We've got the right horizontal asymptote and the right vertical asymptotes. And so when we get to the graph, we just want to make sure it's consistent with all the information we determined before that. And again, what I'd like you to get out of this is the ability to look at a graph and say, oh yeah, that makes sense based on what I know about derivatives. Okay, if you were to plug this in your calculator incorrectly and get some different graph, plug this into a graphing calculator is what I mean, and get a different graph because you entered it incorrectly, you know, what my hope is that you would be able to recognize that, hey, this doesn't make sense. This, you know, doesn't have the right local maximum, or this is not increasing in the right place, or the concavity doesn't seem to make sense. That's what I'd like you to get out of this section, is be able to have that understanding of how the derivative tells you what to expect. I hope you found this example helpful, and I will see you in the next video.